Morning. Now, in this class, we will learn about one of the applications of Fourier transform, which is finite wave train. So, this is just a theory part, and one integration is involved here, which is very simple. So, this is only just a theoretical concept. So, we will go through it. As I already said, finite wave train. It is one of the important application of Fourier transform, and it is nothing but resolution of a finite pulse into sinusoidal waves. That is, if you have a finite pulse, you will resolve it into sinusoidal waves. That resolution of a finite pulse into sinusoidal waves is one of the applications of Fourier transform. Okay, suppose that you have an infinite wave tree. Okay, now that is sine omega 0 t, that is your given function. Okay, let that be clipped by a Kerr-cell or saturable dry cell shutters. That is, you are having a function sine omega 0 t, and by some means you are resolving, or you are clipping that function by means of a saturable dry cell, and on doing so you will have a split up as the given function f of t, that is sine omega 0 t. It will be the function itself for that interval t less than n pi by omega 0, and the function will be 0 for t greater than n pi by omega 0. Omega 0 is the frequency and n is the number of cycles involved in the given pulse, or in general n is the number of cycles involved in the original wave train. See, this is the diagram of that pulse. Then here we know the given function f of t is sine omega 0 t, so it is a odd function. Okay, so we can use sine Fourier transform, and the formula for sine Fourier transform is gs omega equal to, we have already studied, root of 2 by pi integral limit from 0, here the limit is n pi by omega 0, then f of t, here in place of f of t you can write the given function as sine omega 0 t, then sine omega t dt. Okay, what was the formula? Gs omega equal to integral 0 to 2 by pi integral sine integral f of t sine omega t dt. That was a formula. Okay, here for that integral we have substitute the values 0 to n pi by omega 0, and in place of f of t you have substituted the given function sine omega 0 t, then sine omega t is kept as such in the formula. Okay, now here sine a, this one is similar to sine a sine b. Okay, that is omega 0 is a and omega is b. Okay, so the formula for that will be cos a minus b minus cos a plus b by 2. Okay, so replace this with this formula, so you will get the above equation as like this. Okay, just substituting those formula. Then here taking this 2 outside, so root of 2 by pi by 2 will be 1 by root of 2 by pi, then the rest everything that is there in the bracket is kept as such. Okay, then 1 by root 2 pi is kept as such. First apply integral to this one, you will get this, then apply this integral to this one, you will get this, then apply the limit n pi by omega 0 0. Okay, now after that apply the limit, 1 by root 2 pi is kept as such. In place of t apply the first limit, that is n pi by omega 0. Here also in place of t substitute the limit n pi by omega 0. Then when you substitute this lower limit 0, everything will become 0, so that term you need not write. So you are left with only this term. Okay, so this integration is very easy to follow, right? Now, so here we can see that it is of interest to see that how gs omega, that is Fourier sine transform, depends on frequency. Here it was gs omega, right? It actually is depending on only the frequency, that is omega. Now for large values of omega 0, only this first term is of great importance. So you are writing the first term, this term we are neglecting. Okay, that is for large values of omega 0, only the first term is of importance. So you are writing that first term alone here. then 1 by root 2 pi is kept as such, n pi by omega 0 is taken here, then you just multiply and divide this term with the n pi by omega 0. Okay, you will get like this. Now here this 1 by root 1 by root of 2 pi is kept as such, n pi by omega 0 is also kept as such. Now this is of the form limit theta tending to 0, sin theta by theta is 1. So this will, we can take it as 1. So you are left with only these two terms. Okay, so gs omega, now your gs omega equal to 1 by root of 2 pi n pi by omega 0. Now this is the final representation of the Fourier transform of finite wave train. Now this is called amplitude curve, and it is similar to the amplitude curve of a single slit diffraction. Now the above given term, that is the sine term, will be 0 for those values of omega 0 minus omega by omega 0 n pi. For these values of, that is, this you can take it as theta. Okay, so sine theta equal to 0 only when this value of theta, that is this, is having these values, that is plus or minus pi, plus or minus 2 pi, plus or minus 3 pi, etc. Okay, so again rearranging, omega 0 minus omega by omega 0 is kept as such, then here this n pi is taken to this side, so you will have plus or minus pi by n pi, that is omega 0 minus omega by omega 0. This will be plus or minus pi by n pi. Okay, pi and pi get cancelled, so it will be plus or minus 1 by n, plus or minus 2 by n, plus or minus 3 by n, etc. For each value you can substitute like that. Okay, now so we can consider this finite Fourier sine Fourier transform gs omega as a Dirac delta function. Now its contribution outside the central maximum, this is the central maximum, outside the central maximum, that is in these regions, the contribution of gs omega is small. So we can consider this delta omega as a measure of spread in frequency of the wave pulse. So delta omega stands for a measure of spread in frequency of wave pulse. That is, if omega is a frequency, then delta omega will be the spread in frequency of wave pulse. Now if the pulse that you have is large, or if it is a long pulse, that is, if n is large, what is n? Number of cycles involved in the original wave train, right? So if n is large means you are having a long pulse. If it is a long pulse, then the frequency spread delta omega will be small. Okay, so if n is large, that is in the case of long pulse, frequency spread delta omega will be small, and if the pulse is short, that is if n is small, you will have a short pulse. In that case, delta omega will be large, just the inverse. Okay, that is the interpretation of the finite wave train. That is, if pulse is long, frequency spread delta omega is small. If pulse is short, frequency spread delta omega will be wide. Okay, so that is enough. So this is just a theory, and which is easy to follow. So just note it down. Okay, the application of Fourier transform, finite wave train. Okay.